Alright, today we will prove the rank-nullity theorem from linear algebra. So say we have a linear transformation T between two vector spaces V and W. Then we could also say T is a homomorphism between V and W, so it is linear, it preserves the group structure, or the algebraic structure of the vector spaces V and W, and say that it's also finite dimensional. So since V is finite dimensional, and we know that the null space of a linear transformation is going to be a subspace of the domain vector space, we know that the domain vector space, or rather the null space, is going to be finite dimensional, right? Because if the bigger space is finite dimensional and the smaller one's within it, the smaller one also has to be finite dimensional. So let U1 up until UM be a basis for the null space of T. Okay. So any vector U in the null space of T can be written as a linear combination alpha 1 U1 plus dot 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 up until alpha m UM of these basis vectors U1 up until UM. And since we defined it to be a basis, it is a basis, and it's going to span the null space of T, and it's also going to be linearly independent. So, since this is linearly independent, we know the null space of T is going to be m-dimensional. So let's write this over here. Dimension of the null space of T equals m. Right. So now what can we do? V is finite dimensional. Why don't we extend this basis U1 up until UM to a basis of V? So we'll say we get U1 up until UM, and then V1 up until Vn is our basis extension, is a basis of V. So by the same logic, it spans V and it is linearly independent. So then the dimension of V is going to be equal to n. Okay? Because it's just the length of the basis. It's going to be actually m plus n. Sorry about that. So you're going from 1 to m and then from 1 to n. So m plus n. Right. So now, all we have to do is show that the dimension of the image of T, or the range of T, is just equal to n. So let's begin. Since this is a basis of V, any vector in V, an arbitrary vector V, can be written as a linear combination of these basis vectors, alpha m u m, up until, and then we have beta 1 v1 up until beta n vn, right? What could we do from here? Why don't we apply t to both sides of this expression? So we'll get t of v equals t of alpha 1 u1 all the way up to alpha m um plus beta 1 v1 all the way up to beta n vn. Now, what's so special about this? T is a linear map. So it is additive and it is homogeneous. So that's just a fancy way of saying we could pull these coefficients in front and break this up into a sum. So T of V, and this T of V is an arbitrary element of the range of T, since V is an arbitrary vector in V. Right? T of V is going to be equal to alpha 1 T of U1 plus every one of these up until alpha m T of UM, and then we're going to get beta 1 T of V1 plus all this junk up until beta n T of Vn. Now, we're going to see how this is going to start cleaning up, because U1 up until UM was a basis for the null space of T, and the null space of T is by definition the set of vectors in V that get mapped to the zero element of W. So T of U1, T of U2, T of all of the U's up until M is going to be equal to 0. So all of these go to 0. And now we're in the home stretch because T of V, this arbitrary element of the range, is just a linear combination of these vectors. Of Vn. And just looking at this, we see that the range of T is going to be spanned by this set of vectors. So, or we're just going to call it the image in this video. Image of T is equal to the span of TV1 up until TVn. Now that's one of the conditions for being a basis, that is that it spans the vector space. The other one is that it's linearly independent, which we will now show. So say that we have a linear combination of these vectors being equal to the 0 vector. So gamma 1 T of V1 plus all the way up to gamma n T of Vn equaling the 0 vector. By the same logic as earlier, but in reverse, we could leverage the additivity and homogeneity of the linear transformation T to rewrite this as a single application of the transformation. So T of gamma 1 V1 plus dot 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 up until gamma n Vn equals the 0 vector. But just looking at this, we see that then this vector is mapped to 0, so it's in the null space of T, which means that it could be written as a linear combination of the basis vectors for the null space of T. So then we get gamma 1 V1 up until gamma n Vn is equal to alpha 1 U1 plus dot 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 alpha m Um. And now we could just subtract from both sides to get alpha 1 U1 plus all this junk up until alpha m minus gamma 1 V1 minus all this stuff up until gamma n Vn equals the 0 vector. Now, we know that U1 up until and then V1 up until Vn are a basis for V, so they're linearly independent, and these are just arbitrary constants. But since they're linearly independent, we know they're all going to be 0, and since gamma 1 up until gamma n is a subset of this list of just zeros, we know they're all going to be 0. Which means that up here, all of these are 0, which means that the list TV1 up until TVn is linearly independent, and that along with the fact that it spans the range, or the image of T, means that it's a basis for the range of T. And since it's a list of length n, we could say that the dimension of the image of T is equal to n. Now, in the beginning, we saw that the dimension of V was m plus n, and clearly m plus n is equal to m plus n. But n is clearly this, as we have now shown, and m, from the beginning, was just the dimension of the null space of T. So we have thus shown the rank-nullity theorem to be true. The dimension of V is going to be equal to the dimension of the null space of T plus the dimension of the image of T.